We are going to talk about why we need the add-on, the benefits of having a private cloud able to run container technology for your IT services, and we're going to see also some interesting use cases. So this is the beginning, why we did it. We don't really have a data center and didn't have a data center at school. We just had a room with all servers, as you can see in the picture. And the way of operating the IT services at the university were really legacy. Some services were running on the bare metal machines, and other services were running on hypervisors without the orchestration layer that simplified this interaction with the admin and the service. So, and we also had a lot of compute units without virtualization extension. So, full virtualization in those cases was out of the question because emulation is worse. So, having these conditions, you can expect users to complain a lot and IT, that is admins, to work even more under pressure. So we needed to come up with a solution to that. How to achieve a better operation in the services without acquiring new hardware? Because the thing in the university was the hardware wasn't really bought or given by some credits or something. Hardware came by surprise because somebody donated it. Either another Cuban enterprise or a business partner in the overseas trying to get a business opportunity with the island. So the natural response to that question will be to migrate to cloud computing. But as we know, cloud computing nowadays, the mature platforms rely on full virtualization in order to perform the workloads. And we couldn't afford that because we could deploy it in some compute units, but not the whole units we had. So we looked for other virtualization technologies. And it came to our attention the operating system level virtualization, with the benefits of not needing to require the CPU support in order to perform the virtualization, and the very low memory footprint that allows us to virtualize more Linux OSs with less hardware. And the other added benefits of the fast boot time, of the lower latency that came with the lack of hardware regulation. So in this case, there are two variants of containerization. There are the system containers and the application containers, being the most prominent solutions in those cases, the LXD hypervisor and the Docker. The difference is that the system containers are full Linux OSs almost exactly as an OS that you could expect from a virtual machine or from a real server. And Docker just runs ephemeral containers and without data resistancy, and well, you can save data with external volumes, but we really needed to keep the same perspective of an operating system versus admin, because if they were going to operate a proxy or a DNS, they are used to run the services inside a full Linux OS. So we needed LXD. In order to reassure our selection, we seek for benchmarkings a test that compare the Linux containers versus the hardware virtual machines. So Canonical made this test, I don't know, I think it was in 2015, where you can see as LXD runs far more containers than virtual machines with the same hardware, up to 14.5 times greater. And this means that you can achieve a higher container density, and also that the memory footprint of the container is very low. We ran the test by ourselves, and we looked at the memory footprint, and it was like from 16 to 32 megabytes per container. Also, another metrics came out of that test, because the boot time of a container is more or less like 1.5 seconds. So full Linux OS boots up in just that glimpse. And with all the machines that were launched, they finished before launching the virtual machines and KVM. So it was a really nice figure. So next thing we were looking for, well, cloud computing. How well does Linux containers are suited for cloud computing? And the answer is that the container technology, at least the full system container technology, is very poor on the mature platforms. OpenStack being let's say the standard for cloud computing open source technology, had a really poor support for LXD or LXD, which is the higher abstraction layer for Linux containers. So LXD is not really recommended, because it runs through the Libvirt, and if you look for the documentation of Libvirt, it is really poor, has a really poor interaction with the LXD. It lacks a lot of features. And no LXD, it's also very green. This is due to the fact that OpenStack is a really big complex system, and maybe integrating things to OpenStack takes longer than to integrate technologies to simple cloud platforms. So we looked for other solutions, and to our attention came the CloudStack and the OpenNebula platform. CloudStack seemed like a bit dead for us, so OpenNebula, it looked very nice. A simple cloud platform with such a good ecosystem, with add-ons, with the development documentation, very easily to digest, to interact. And we decided to develop an add-on for OpenNebula in order to drive LXD. So this is the overview of OpenNebula, just the core where the magic happens, and system interfaces and user interfaces in order to interact with users or other higher abstraction layers like Amazon EC2 or Azure, and the different subsystems, the virtualization, networking, and the monitorization drivers. So there are a lot of users of OpenNebula, so we didn't want to have something that was rarely used, so it would be dead, but that was not the case. A lot of people use OpenNebula. And after reading the developing documentation, we looked at the system interface, and we realized that we just needed to operate over the VM API and the IM API, the virtualization and monitorization interfaces, in order for OpenNebula to be able to talk to compute nodes using LXD. So it was a very simple section that we needed to adjust instead of having to touch more of the system. So we did make an add-on before using LXD. It's called LXD1 instead of LXD1. But it was our initial implementation. We can say that it was really poor. But instead of besides for being poor in terms of implementation, the code wasn't very nice. Adding new features to the add-on was very difficult due to the poor implementation. Besides that, it did the job. OpenNebula was able to drive Linux containers, but And we also had it on production in our data center. This is the GitHub repository. You can check it. It is archived right now. It is unmaintained. We don't really recommend it. So, with the arrival of Ubuntu 16.04, LXD launched its first stable release version. So we thought that, hey, why don't we make an add-on, better add-on, than just LXD, because LXD adds a lot of value to LXD, like a simpler user interface, simpler container management, new features like live migration, and other storage backends, a lot of things that add value to the Linux container technology. So we made that. It is a better implementation. We use the REST API of LXD through the Python client, and in LXD 1 we just use the CLI, and it has some nice features. For example, in OpenNebula we try to make the life of users that were ready to test this in their virtual environments or in their servers if they want to have an ease of use. So we made a virtual client for OpenNebula, in the OpenNebula marketplace, that you can just download and test the add-on after you, of course, set up the compute nodes. We also made a better documentation for this add-on, and we have had a lot of community acceptance. We have had code contributions with new features added, coming from those code contributions. One day we opened the GitHub repo, and there was like a pull request with a lot of documentation added to the project. It was really nice, and we also have had feedback from users and enterprises that tested this add-on in their servers. And we also have had GitHub issues regarding what we needed to correct, and it is very nice to receive that feedback from people. Right now, our server room has improved a lot, and we don't really need Linux containers to run our services. But the thing is, we don't really want to go back to full virtualization, because containers are very nice. The boot ups, the memory footprint, the ease of use of the hypervisor, LXD is very nice. So we just use the KVM machines for non-Linux OS or Linux modified kernel OS, such as the FreeBSD, which is not Linux. We need, for example, to run our pfSense to the internet gateway. And we also have this compute environment running over our set storage, which also runs on commodity hardware.
Hi. We actually wanted to make a live demo for you to be able to see what we have done and how it behaves, but we couldn't bring the hardware with us. So kindly, the people from HPC now, they find us the hardware, and we just broke the software, and it didn't work. I'm so sorry about that. No idea if the micro SD card got corrupted, or I don't know, perhaps it's the SPC. But the idea was to test this platform in a really limited environment. And for that, we got this. This is a Raspberry Pi. As many of you might know, there's only 1 GB of RAM here, and the processor is a Cortex A53. Oh, I'm sorry, you should trust me on this. We have tested a lot, and it runs pretty well. We will show some benchmarkings after. And the interesting part about this deployment is that it's deployed the same way as in our data center. And we're using actually OpenNebula, the orchestrator, in one LXD container. So we have this container managing the same node where it's deployed and managing other nodes, of course. And right now, well, we have several containers running here, but we'll skip this part. So in this part, we are not an isolated case. I mean, cloud computing benefits are well known by everyone, and this has driven many companies to migrate their services to the cloud, as shown in this survey from Price Help. And it says that 92% of companies deploy their services, they migrated their services to the cloud. But the interesting part here is how they're using the cloud. I mean, 21% of the companies are using only public cloud. In the meanwhile, only 4% of the companies are using only private clouds. But there are disadvantages with public clouds. In our opinion, the main 3 disadvantages that you can find in public clouds are, first, we have security. Your private data will need to leave your facilities to end. There's sometimes you know, sometimes you don't. Second, you have cost. A lot of time, at the end, in a really long run, you end up paying more if you're renting services or you're renting infrastructure against to deploying your own infrastructure and maintaining it yourself at home. And the third disadvantages that we consider really important is that you really don't have control about the platform. I mean, you have to adapt yourself to the platform and the services that someone is providing you instead of adapting the infrastructure to your needs. So we wanted to change this. We wanted to give companies, mainly small and medium-sized companies, which are the companies that most use public clouds, a way to deploy their own private clouds inside their own data centers to break dependencies with public cloud providers. And for this, we knew we have an efficient project. We knew we could reduce costs of deploying private cloud solutions. But we also knew it wasn't enough, because private clouds right now, they are really expensive to implement. At the beginning, you need to acquire all the hardware, and it's really complex to maintain, which translates in high operational expenses and high capital expenses. So these are the elements that contribute to this the most. We have server costs, high availability, because even if you have enough power to run your workloads, sometimes you need to buy more hardware just for this task. We also have a high power consumption for most of the hardware. We have the complexity of installing everything, and we also have the difficulty of maintaining this quality. And for that, we developed Flux. Flux is nothing more than this project take to the other level. And Flux is mainly what we brought you today. This is an SPC right now with all of the hardware, all of the software that you need to run your private cloud. Mainly, Flux is an open source solution to provide simple, efficient, and low cost ARM-based private clouds. It's completely open source. There's no cost associated at all. We don't charge for anything here, even for support. We just help the most we can and hope for the best sometimes. So how does Flux manage this? Well, Flux uses LXD, uses OpenNebula, and is powered by ARM architecture. And this allows us to improve the efficiency, improve ease of use. Also, we have a great scalability. We have technologies that are really proven. It's important to say that Flux is not limited to this. Flux might use also KVM, because OpenNebula supports KVM, and of course it can run on AMD64 hardware. But it will lose a lot of non-functional requirements that we were seeing. And how do we improve ease of use? Actually, what we did was to use create the platform, install everything we needed, and to provide a typical case that will fit most of the small companies. And we made this deployment for 2 single-board computers, Raspberry Pi 3, and Pi 64. Actually, right now Pi 64 has a better support for Flux than Raspberry Pi 3 also has a better hardware. So we recommend it. There you can see our webpage. You can go check it, perhaps install it yourself. And this is how it should look. This is what we are building right now. These are boxes with 5 single-board computers inside. And we also have ideas to develop 15 board cases and 25, but this is what we are working on right now and trying to finish the cases. This is more or less how it should look with a DC power supply, because our power supply is custom. So if you can find a custom power supply, you can develop it yourself. So you simply use a DC power supply. And besides private clouds, there are other approaches that can be used with this technology. Right now, in the field of HPC, we can see that this is the top 500 supercomputers, and we can see that the first two are currently reaching the 20 kilowatts overuse estimate. Actually, in the future, it's estimated that it will get worse. Perhaps we will reach the megawatts level. Once we reach exaflops, perhaps we will consume several megawatts. And there is a lot of work being done in this area, how to improve efficiency on HPC. And one of the approaches that the community is following is trying to use air-end power. We saw a great comment about this. If it's going to work, if it's not, no idea. But we have seen several works with air-armed clusters, like the one from Valentin Plugaro. He's a professor from the University of Luxembourg, and one of our inspirations to follow this project. And he developed, for example, a cluster with ECX 1000 servers. So over this, he deployed infrastructure as a service capable private cloud platform, which shows OpenStack, and it's a common use even in these really small scenarios. And he used LXD. So his results, many of the results that we have seen, this is just an example to illustrate. He got a 20% drop on computing intensive tasks and 65.6% drop in communication capacity. These are big numbers. It's really inefficient, so you will lose every aspect that you're trying to improve. So we knew we have an efficient platform because we manage LXD container in a different way, but it's not enough to sync it. We have to measure this. After this, we built a small cluster. In our cluster, we used 5.64 single board computers, and we're actually running our workloads, which will be inside containers, on an NAS drive, because the micro SD cards are simply too slow, and IOPS are not high. So then we tested, and these are our benchmark. We just chose a couple of these. We have more metrics here, but more or less they all follow the same line. And we got an efficiency from 95% to a 99% level, so greatly increasing efficiency against the other approaches that we had seen. So perhaps it could be scaled. Perhaps there will be limitation with when scaling this. This is one of the things we want to try. And there are also other use cases, and one of them directly has, it happened to us. We wanted to research on cloud computing, but we currently have two approaches. We could either use simulators, that they are not so accurate, or we could deploy testbed. But this is not only our case. Also is a case with many universities and many research centers, because even testbeds are really expensive, and they don't quite get the amount of node that you will end up using. So you can trust these testbeds either. So a good approach would be to use less cheaper nodes, like this one that we got. And the other use case, is one that we're working right now, is on edge and fog computing, mainly on fog computing. There have been a lot of development in this area, and a lot of approaches, but there doesn't seem to be a consensus about what platform to use. I mean, they all talk about fog nodes, everyone talks about cloudlets, but how should it be? Which architecture will it use? How will it interact inside the fog node? So there is a lot of disagreement here, and we believe this is an approach that could work in this area. So according to this is our roadmap. We are going to keep integrating with OpenNebula to keep adding support for a lot of features that work with KVM. We also want to add support on LXD, a better LXD line interaction to try to manage LXD container as it should, because in a lot of aspects, like concept, support is not enough for us. We had to make a little modifications there, so we will try to keep improving that. Also, we want to support a greater variety of guest and host operating system. Right now, we support only Ubuntu 64 because it's the platform that we use. But here in Europe, there is a lot of companies and use cases using CentOS. So we also want to migrate there. Actually, there is a user that is currently helping us with this, trying to improve the documentation to support CentOS cases. And, well, generally keep working with OpenNebula. So, thanks for your time. Any questions?